Hi Gidlets, this is your fifth section of notes on the properties and functions of telescopes. So as you will see, there are three general properties of telescopes that are really important for viewing astronomical objects. The first is light gathering power, the second is resolving power, and the third, which is most notable but also least important, is magnification and magnifying power. So we can think about telescopes as being light collecting buckets. So just as you have, say, a bucket which collects rainwater, the bigger the bucket, the more rainwater it's going to collect. Well, photons of light are the same thing in terms of telescopes. So the bigger your light collecting bucket, the more light that you are going to collect. So we increase the diameter, we increase the light that gets in. So this is just your diameter squared. So if we had a, for example, 40 centimeter telescope, it's going to collect a lot more light than we would with a 20 centimeter telescope. So resolving power is our second desirable characteristic of a telescope, and this is really important. So our light collecting power, our ability to see faint objects, and also our ability to separate closely spaced objects in the sky are the two most important functions. So just as our light collecting power allows us to see really faint things, from our line of sight we may see two different objects very close together. So for example, if we see a star that is 5 light years away at this point in the sky and one 1,500 light years away at this point in the sky, depending on the resolving power, our eyes may see this as one blurry object. So if we take a look at this image here, we can see here we have one thing, what looks like one point of light, and we have these rays radiating outwards from it. And then we have here, you can start to see the differentiation or the separation between two distinct objects. So in terms of resolution, and if you're interested, here is the math behind that. Our angular resolution is symbolized by an italicized lowercase a, but our resolution, we want to be very small. So this would be a very small number. So light collecting power would be a large number because bigger is better, but resolving power, we actually want a very small number to be able to separate closely spaced things. So the lower our number for resolving power, the increased ability we have to see that fine detail and to see individual objects from each other. So here we have an example of what that would look like. Here we can see what looks like one point source, and here we can see that definitively there are two point sources. So this would have a very high resolution. So magnifying power is our least desirable property of telescopes. But this is something that if you were to go into, say, a hobby shop or Walmart and ask for a telescope, they would tout the telescope's ability to magnify large objects. But the reason this is not such a great thing is because if you have a big blurry object, magnifying it is just going to make it a bigger, blurrier object. And it'll also make it fainter because it's going to disperse the light over a wider area. So your object, which was all, say, concentrated to here, is now spread out over a much wider area, which disperses the light and actually makes it fainter. So this is a function of your primary lens, or your primary diameter, and your eyepiece. So it's a ratio of the two. So magnifying power is important, but our resolving power and our light gathering power are far more important. Magnifying power without those other two means nothing. We've just magnified blurry things to bigger blurry things. So here we can see again some of the effects of some different resolutions. So here we can see telescope A. We can see that this is a very blurry, looks like galaxy, and as we're getting to smaller and smaller angular resolutions, we can see that these images sharpen. We can see much more distinct, fine detail. We can start to see the halo of gases around the galactic center. We can see some spiral arms, some gas and dust, and we can clearly see a lot of the surrounding stars. So here is a function of telescope size. So this would be our light gathering power. So B would be one that is twice the size. We can see that it makes this object look much more clear. It looks much brighter. If you were to look at the actual brightness of object B, of this galaxy, and comparing it to A, because this is a larger light gathering power and diameter of the primary lens, you can see it actually looks brighter. So light gathering power over magnification, even though it looks as though the image was magnified. So one of the questions that I would want you to be able to answer would be which telescopes would allow you to see fainter objects. So would you want a small diameter? Would you want a large diameter, or either, as long as there's good magnification? So please make sure you can actually answer that question. And then also thinking about the advantages of space-based telescopes. Think about which of these functions is altered by the atmosphere, which would be much easier done in space. Would all of them be easier if done in space? So one of the ways that astronomers are able to get much clearer images is by using something called adaptive optics. And this is a technology that your cell phone also uses, but this is invented for the use of telescopes in making very faint, very distant objects appear clear. Because just as your cell phone camera is picking up pixels of different objects and converting those into an image, that is exactly what a telescope does. But telescopes have been doing this since the 70s, and this didn't hit the cell phone or communications world until a couple decades later. So adaptive optics take a pixelated image such as this, and the way we can think about that is whatever the receiver is having a bunch of teeny tiny little things called bins. And as photons hit those, the photon counts are converted through the photoelectric effect to electrons, and those electrons to energy, and it sends a signal. So say the photons, or the bins that are in this area, have collected far more photons than these, we would get a centrally bright area. And here you can actually see the different pixels, and it gives it a value. So the higher the number, the higher the photon count. And then through converting it through these computers, we can then see this brighter object here. And same with these images. So this is a set, and then this would be a set. So two different things there. So this used to take a really long time. This could take hours to convert a single image. And now this is done instantaneously. This can happen hundreds or sometimes even thousands of times per minute. So CCD imaging is actually the specific technology that is used in your cell phone, and this stands for a charged coupled device. So what we used to use, just like Edwin Hubble used, was photographic plates. This is the old style of imagery and photography, but CCDs are where we use those bins like I just talked about that collect the number of photons, and each of those photons are given a value, and the area with the highest value would indicate the area that is the brightest. So this can be read under the computer memory, and this allows for manipulation of data. Here we can see, it looks like the Sombrero Galaxy, and here we can see in the bottom an infrared image of it. So, you know, two different wavelengths using the same technology. So both using CCDs, because we know that all wavelengths have measurable energy, and we can measure how that energy hits each of these bins in counting the number of photon hits, and that then is converted to a numerical value, which is converted to an image. So it's a multi-step process. So here is what one of those arrays would look like. So when I was in grad school, we had to actually calculate what the photographic ability of these things were. So here are each of the different bins. These are called an array, and there's a value you can give those. Those are then sent to the edges. Here is where those are read. So here we have one edge, which then sends it to over here, and then here is where that information is read out. And this would be what an actual picture of that would look like. So here we can see there's 0 photon counts out here, and towards the center we have a much higher count. So here would be the point source, here would be another point source. So here we can see what those pixel counts would look like. And this is utilizing what Einstein discovered, which was the photon or the photoelectron effect, that wavelengths of light can be converted to energy. So we're going to look at some different modern day telescopes. Here we can see this is called a Newtonian. You don't necessarily need to know this, but I just wanted to expose you to some different ways that light can be gathered, some different ways that these very distant images can be taken, and from ground level, and how this would work. So here you can see your secondary lens, your primary lens, your eyepiece being way out here. This is what a lot of observatories have. Very, very large light collecting power because of an increased diameter. So this is called a Schmidt-Cassegrain, and what this does is you have a couple different mirrors that then you have your light traveling multiple passes throughout this, so you have a lengthened focal length, and the longer the focal length, the higher degree of detail one is able to see. So this allows you to not have a 30-foot long focal length, or a 30-foot long telescope tube, but you can still have that long of focal length. So here we can see a traditional mirror. These can be extremely heavy, so here we can see the path of the light. So this guy is in is at NAU. This is near Flagstaff. So here we can see this is an open truss, so it does not have an enclosed tube, but it is surrounded by a dome. So we can see the secondary mirror is very large, so notice the size of the dude so that you can see for scale. So here we can see some big changes in ways to make these different lenses, ways to make these different mirrors. And one of the most obvious is segmenting. Because if you have one of these things, and say you have a diameter of 30 meters, which is pretty large, if you have a failure in any of these areas, that's going to affect your overall image. So for whatever reason, it took them a long time to have the technology to be able to make segments where you can replace individual components. You can work on individual components, whereas here, that's really difficult to do. So one of the other very simple ways, we have something in my classroom that looks like this, altitude azimuth mounting, where it just goes up and down. Equatorial mounting allows for multiple different movements along the axis of rotation. So here we can see a segmented mirror, the whole team that built that, as compared to this. And here we can see some examples of some very large, very expensive telescopes. And they all have super intelligent names, you'll see. The Grand Telescope, there's another called the Very Large Telescope, which is right here. There's another one that's being built that's called the Extremely Large Telescope. This guy is the Large Binocular Telescope. It kind of looks like Wall-E. So this guy has diameters that are 8.2 meters. This guy is in Europe. This one has the segmented mirror. Here's the Magellan Telescope. Here is a person for scale. So you can see that all of these have domes around them, so they're protected from weather. So that protects the telescope, but remember these are only functional at night, not during the day. And these would also be affected by adverse weather. So there would be many months that a lot of times these may not work because at high elevation there can be adverse weather. But putting them at higher elevation in drier climates, so deserts, is really preferable to maximize the viewing conditions. So this is the 30-meter telescope. Take a guess at how big that primary mirror is. This is the extremely large telescope that's 39 meters. They apparently have super creative people that name these. And this is in the process of being built right now. And it'll have 798 segments to that mirror. And here are some people for scale. So Mauna Kea, this is a multinational effort on top here. So we have telescopes owned by the Japanese, by Canada, by Europe, by the UK, by the European Space Agency, and each of them have different research areas. So this would be ours, there's Japan's, this is our infrared telescope. My advisor from grad school is there right now doing a bunch of asteroid detection research. And here we can see the opening and closing of the domes. We'll see this at the observatory as well. Here, the Very Large Telescope in Chile. And we will watch this video in class. That is it for now, guys.